Excellent. So, welcome everyone. So this is the fifth session in the Cohesa seminar series. And thank you very much, Professor Wilton, for volunteering today to present. Now, the theme is still basically get to know each other, but we're hoping that starting June, we're going to be getting some short progress updates as well from the participants. And at the end, I will just remind everyone of what the next upcoming seminars, who the presenters are, basically. Okay, so if you're ready, we can begin.
Yeah. All right, so let me see if I can do this. I hit share screen, and then this.
Perfect.
All right, so now you can see, let's see if I run this. So now you can see the slides?
Excellent, yes.
Okay, good. All right, oops, let me go back. There we go. Okay, so thank you for being here. Basically, as you said, my plan today is just to talk a little bit about some of the research that I've been doing, and in particular, how I think it relates to Cohesa and how we're going to go forward. So these are many of my students. These aren't all Cohesa students, but a few of them will become Cohesa students. So my work is in FPGAs, field programmable gate arrays, and traditionally FPGAs have been really good for prototyping hardware, but that's actually not all they're used for today. FPGAs are now being used in the data center in the cloud. So Microsoft has FPGAs in their cloud. Amazon has it as well, and there's others that have it as well. And so the plan is that FPGAs can be used for compute-intensive applications, ideally in the cloud as if they were just normal compute units. And one of the promising applications is machine learning, which is why Cohesa is appropriate. My research in the past has really been focusing around FPGA technology, and some of the type of questions I've been asking. Basically, a lot of it has to do with programming or designing applications on FPGAs. In the past, that's been Verilog and VHDL, but today it's HLS-oriented techniques, and there's other techniques as well. Been focusing a lot on how to optimize and debug, and I'm going to talk a bit about that today. I've spent quite a bit of time looking at new architectures for FPGAs, in particular chip-level architectures. So actually, my PhD was on memory. My PhD was at University of Toronto on memory architectures for FPGAs, and I've done things like low power and other things. Compile time is an important question. We spent some time on that, and we haven't really talked about new design flows, but that's important too. So all of this is related to what I've been doing, and the goal is bringing FPGAs into this new world where they can be used for these heavy compute applications like machine learning applications. So this I think just repeats some of what was on the previous slide, some of my recent research projects, just to give you an idea of where I'm coming from. So I've been doing a lot of work on debug and verification, and the early work actually led to a startup company that was acquired by Tektronix. Since then, so I was away from university for a year and I came back, and I've continued working on debug and verification in parallel. The company is not there anymore, but the technology is still going. We've been generalizing that to a design ecosystem, and I'll talk a little bit about that too. So initially it was debug and optimization, but there's other things we can do there. And in particular, it's interesting if we look at HLS, or high-level synthesis techniques. And again, I'll talk a little bit about that because I think that leads into a lot of the Cohesa work that I want to do. And in the past, that's being done with Intel, and I will continue that. But I think there's probably a lot of other interests within the Cohesa network as well. I hope so anyway. FPGA CAD, I've been spending a lot of time on that. And the big question I'm looking at right now there is is runtime. So FPGA CAD tools are really too slow and memory hungry. And so we have a current project on incremental compilation techniques. So the FPGA tools do incremental compilation, but there's a long way to go. There's a lot more we could do there. And so I have a project based on that. FPGA architectures, as I said, looking at how to build better FPGAs, not use them, but how to build better FPGAs. And one of the questions there, especially if we're putting these in the data center, is power efficiency. That's really important. And there's a lot of things we can do related to power, and then maybe domain-specific type architectures. So perhaps an FPGA oriented towards machine learning. We haven't been working on that, but that's one of the things I would like to do. And then this last one is sort of unrelated to everything else. We've got a project with D-Wave looking at quantum computing. I don't quite see that. That's still preliminary. I don't know that we'll be expanding on that into Cohesa type applications, but we'll see what happens down the road. Okay, so that's what I've been working on. The relationship to Cohesa. So obviously, or as I've indicated, FPGAs can provide rapid hardware acceleration. Hardware is going to be faster than software if it's done properly. Not only do you get better parallelism, you can optimize the data paths for exactly what you want. So you can get significant performance and power improvements compared to doing things in a GPU or CPU. The challenge is that an FPGA is hardware. You're programming hardware. And designing hardware is time consuming, it's expensive, it requires expertise. Certainly a lot of domain experts that want to investigate implementations of machine learning algorithms don't want to be sitting down and designing Verilog and VHDL and worrying about time enclosure and all these other complicated things. So what would be very valuable, I think, and would make FPGA technology a lot more accessible to a lot of other people in the network is if we can provide a framework or ecosystem that provides the ability to prototype or design hardware acceleration. So I just want to make this distinction here between prototype and design. As I said, in the past, FPGAs have all been about prototyping, and we can do that. So a lot of the things that the architecture groups are doing, Andreas and others, they very well may want to prototype some of their designs on an FPGA, and we can do that. But I think there's a lot of value in just targeting an FPGA as an FPGA, not prototyping it for something else. And that makes a lot of sense when you want the speed of hardware, but you don't actually want to build a chip. So I think both of those are important targets here. Now, this framework or ecosystem, I guess it's always good to have sort of a dream goal where we'd really love to get to, is we'd love to have an ecosystem or framework that allows domain experts that really have no interest in hardware to prototype designs. Now, hopefully domain experts are at least software designers. If they don't design software, then it may be hard to provide that. But ideally, we take these experts that can write software, don't care about hardware, but can still give them the benefits, the power and performance benefits of going to hardware to an FPGA. And okay, that's sort of a dream goal. Maybe we won't quite get there. I'll talk a bit about that. But the key to get in that direction, at least, is abstracting the hardware away from the designer as much as possible. And so that's a lot of what we're looking at. Okay, so abstracting the hardware away, well, that requires thinking about the difference between hardware and software. And I think everyone here probably understands that. Software, faster, lower power, but a more complicated development process. In software, the big thing in software is that you don't have to think about timing. The scheduling that is done in hardware, that's actually, you have to think cycle by cycle. And that's the biggest difference, I think, between software and hardware. The other thing is there's lots of software designers. So there's lots of machine learning experts that can write software and can write good software. Probably a smaller number that are interested in learning how to design hardware. So we'd really like to provide this software view. Now, in doing that, it's actually quite challenging because software designers and hardware designers have different expectations. Hardware designers and anyone that's been using hardware CAD tools knows that there are bugs. They're sometimes difficult to use. They require a lot of expertise to get right. Things like timing closure just requires a lot of understanding about what the hardware is doing and how to make it faster. Software designers, on the other hand, they're more used to a more mature ecosystem. They expect things like incremental design flows, things like make files that really do a good job of only compiling what's changed without having to go into a lot of detail in the CAD tool. Quick turnaround times. So when they compile things, they want it to compile quickly, not take a day. So FPGA compilations can often take a day to compile. And I know when I visited Intel, they called this a go-home event because you'd compile your design, you'd go home, you'd come back in the morning, and you'd see how well it worked. Well, the software designers aren't used to that, and they won't accept that. And then there's just all sorts of other tools that software designers use. Everything from looking for memory leaks to complicated debugging GUIs to optimization algorithms. There's a lot out there that software designers expect, and we should be providing that sort of thing to the designers if we actually want software designers to use FPGAs. But that's not it. That's not all of it. The other thing is we have to speak the same language. So if I want software designers to be able to use FPGAs, I better not be talking about clock cycles and timing closure. Even if they understand it, they don't want to. That's taking away the advantage of software. Now, one of the tools, and there's been a lot of effort into this, is high-level synthesis. So high-level synthesis sounds wonderful. Ideally, it will convert software to hardware. You just press a button and you get software out the other end. In practice, it's a little more challenging than that. There's all sorts of optimizations you have to specify, and there's people working very hard on this. So we've been involved a little bit in the development of an HLS tool. In particular, leg up that's being developed at U of T right now. One of my students has been working on it a little bit, although now a lot of that is being done in their company, so we're not involved in that. But there's still a lot of work to do there. But the compiler's not enough. Software designers expect a complete ecosystem, as I said, involving testing, debugging, optimization, and really importantly, understanding how when they write the software, it affects the circuit. Because if a software designer wants to optimize their design and they change their software, well, they got to know how this is going to affect the performance of their final design. And so we need an ecosystem with all that in there. Now, we've been spending a lot of time on debugging, and I know that at U of T, you've been spending some time on that as well, so hopefully we can speak some of the same language anyway. Debugging hardware, there are hardware debug tools out there, ChipScope, SignalTap. We teach these in our third-year class, and so there are people out there that can use them. And they work very well. The problem is when you debug a design using one of these tools, they're hardware debuggers. And so they show results in terms of waveforms. So if you show this waveform to a software designer, well, they're not really going to quite know where to start. And even if you show it to a hardware designer, they don't necessarily want to look at that and try to figure out what's going on. It's even more complicated because the HLS tool does all sorts of optimizations. So it moves things around, it changes, it does scheduling, things happen in certain cycles that maybe you didn't expect when you wrote the software. So kind of back annotating in your mind from the waveform to the design can be very, very challenging. So even if HLS is going to be used by hardware designers just to improve their productivity, this is difficult. But if it's going to be used by software designers, this really is not appropriate. This next slide is actually a different tool. So I mentioned that I'd started a company a few years ago. It was called Verde Systems. And so we had a debugging tool, and this is a screenshot from our tool. And, if you look at it, as we see signals, we see sequential, we see blocks, we see, if you look in the bottom left, you see LUT cost, RAM cost, all these hardware-oriented things. And so again, this really was a hardware-oriented debugging tool. Now, it was actually very interesting when we were at the company, a HLS company came to us and asked if our tool would be suitable for their users. And so we thought long and hard about it and realized, no, probably not. And as a startup, we couldn't really do that. So then we said, okay, well, that's an academic project. So then when I came back to UBC, I started working on that. How can we make something like this accessible to software designers? And so over many years, we did develop a framework. And a few things about this framework. I'm not going to go into great detail here. I don't think, if people want more information, I'm happy to talk offline, one-on-one about this. Basically, it's first a couple of things. First of all, it's source level, and that's important. So when we're debugging in the context of the original source code. So if you look at the GUI on the right, that code in there that's probably too small to read, that's actually C code. All right, so you're actually, it looks like a software debugger. You can kind of single step through C code. There's a few hardware-oriented things. You got a Gantt chart there. You're looking at variables, and those are user-visible C variables, not necessarily the hardware registers. That's the thing on the right. So it kind of looks like something like GDB, something like a software designer would like. Another interesting thing about this is that it's really in system. So for a lot of hardware designs, single stepping like you might do in software may not be sufficient. The reason is because lots of bugs don't actually come up until you've been running these things for a long time. Just as an example, let's say you have some bug in a design that's your processor is, you have a processor on your chip, it's implemented on FPGAs, booting Linux, and then something bad happens and you want to figure out why. Well, you certainly can't single step through booting Linux, and you can't even simulate it. If you did, so we did back of the envelope calculations here, simulating at the circuit level an FPGA as it boot Linux would take about 2,000 years. And so that's completely infeasible. So we have to be running these things on chip, in system. And second, we probably want to look at real incoming data. So a good example of that is, imagine we're building some sort of, so Cohesa, there's a lot of interest in visual recognition systems. Yeah, we could maybe, if runtime isn't a problem, maybe we can make a test bench with some image, some video and some images, but we don't really know what's happening unless we have it in chip running at speed with real visual data, real video. And so we do want to run these things at speed. So the way this framework works is we run the design, but we record things in on-chip memory. This is sort of what Signal, Tap, and ChipScope do. And then in the GUI, we actually replay what happened as we were running at speed. So we do have a mode where we can single step in the GUI, and actually, we play with the clock of the FPGA so we can actually single step, but that's not the goal. Or the mode we really like is the replay mode, where we replay based on the history of what was stored in memory. Now, to make that work, of course, you got to store a lot of stuff in memory, and on-chip memory is not, well, there's never enough of it. Let's just say a few words about the GUI here before I get into the instrumentation. So yeah, as I said, I won't go into details, but it looks somewhat like a software debugger. Of course, things do happen in parallel because the HLS tool has processed this, and the GUI knows that. We actually get some information from the HLS tool that we send to the GUI, so it knows when the schedule when certain operations happen. Yeah. Now, I was talking about the limited memory. So what's really important, and actually the biggest part of this work, was the compressing the data, compressing the stuff we're storing in memory. And so we have this is the instrumentation we add to the design to do that compression. And again, I won't go into any details here, but the interesting part is this is constructed on a circuit by circuit basis. So based on the schedule of the circuit, we know when things are updated, and we can use that information to store, to know when to store data. And then we can do all sorts of compression and interesting things, but it's all based on the schedule of the circuit that we have from the HLS tool. And that's something that SignalChap or ChipScope or the software we had from Verity couldn't do. Because we weren't coming out of an HLS tool, we didn't have that scheduling information. Now, okay, so we've done lots of thinking about how to add that instrumentation and how to use it. One of the challenges we had is that version, when you add the instrumentation, you have to then place and route your design. So you add it to the RTL after the high-level synthesis tool, then you place and route, and that's this go-home event. That's slow. That's hours, a day, who knows. Now, the reality is you probably don't just run it once and find the bug. It probably doesn't work that way. What you actually do is you run it and you look at the results and you say, oh, okay, I kind of understand what's going on now. Oh, but if I could run it again and maybe look at some different variables, because we probably don't store them all, or maybe I want to focus on a different function, or I want to stop it at a different point, then I could run it again and get more information, run it again and get more information, and then eventually, oh, okay, I know what the problem is. It's probably not an AND gate or not an OR gate, it's an OR gate when it shouldn't be, or something like that. It's probably something you might have misunderstood, some specification or something like that. This is the way software debug is done, right? You look at the debugger, you run it through, you figure, okay, now I understand what's happening, and then you can go and fix it. The important point is there's many of these debug iterations, and in that initial design, it required place and route for each iteration. So we've looked at all sorts of different ways to eliminate that. And the way that's sort of the most interesting is the concept of an overlay. So what we do is we build this instrumentation, but we make it flexible enough that it can be configured at runtime. So the instrumentation is compiled with the user design at compile time, and that's really slow. That's normal compile time for an FPGA. But then it turns out that the overlay is flexible enough that we can change things like what variables we're looking at, where we want to stop at runtime without having to recompile. So we spent quite a bit of time, and this is some of the more recent work, thinking about what this overlay should look like. There's a trade-off between how flexible it is versus what the overhead is. And I won't go into the architecture or the results in here, but I'm, again, happy to talk about this offline if people want to understand that a little bit better. What I want to do instead is sort of focus on how we would go forward with this in the context of Cohesa. So this previous work, this overlay, was not designed with machine learning in mind. It was designed just for generic circuits. We weren't really thinking about what the circuits are. If we know they're machine learning type-oriented circuits, perhaps there's a lot we can do. Because debugging machine learning is actually, applications are actually quite different. Think about a neural net. Individual wires may not have, it may not be immediately clear what each wire means. That's the whole thing of neural nets. You train it and maybe you can figure it out. You can figure out the cause or the reason for how it's learning, but maybe you can't. Very often, statistical evaluation of behavior is what you actually want to do. You'd like to, for example, as you're debugging the machine learning, you notice that almost all of your activations are going to 0. And that tells you something. That tells you maybe there's something wrong with your nonlinear unit or something else is happening. And that's not just looking at one variable and tracing through. That's kind of getting some statistics about what's going on. And our overlay doesn't do that right now, but it could. Relating what we're looking at to input samples. So this is a little bit different way of looking at it. In the past, we relate everything to source code, and we can single step through source code. But if we have maybe a very pipelined implementation of some sort of neural network, it's actually more interesting to think about how what we're looking at is related to the input samples, because the code itself is actually pretty simple. And so that would sort of change what our GUI would look like as well. So one of the initial tasks we want to do actually is creating an ecosystem like we have here, but targeting machine learning applications. And so this is something we've just started working on. We had hoped that we would be publishing papers by now, but it turns out to be a much bigger job than we had anticipated. One of the challenges is just getting enough example applications and understanding what sort of bugs are common. And so we're working with people to get that information and help build that up. And this is also something that through the network we can probably get help with. But we think there's great opportunities here, and can make these FPGAs a lot more suitable for people that want to use them for implementing machine learning applications. Now, it's not just debugging. Optimization is kind of debugging, just sort of performance debugging, I guess. State of the art right now. So this is actually some code that I got from some people at University of Sydney. And if you look at the original code and you look at the code in the bottom right, you can see things like unrolling loops, array partitioning, pipelining. All of these things had to be added to the code manually to cause the HLS tool to optimize the code well. Well, that's pretty difficult, certainly for a software designer. I'm a software designer, HLS, pipeline, II equals 1. Okay, well, a hardware designer probably understands what that means. A software designer might, if they understand pipelining. Array partitioning, HLS unroll, all these are probably familiar terms, but what they mean in a hardware context may not be clear. And even to a hardware designer, it's not necessarily clear what you should unroll or how much you should unroll it. All these things, there is work on automatically figuring these out, and that's really interesting. But our initial first step is actually not that. It's actually more about providing the information to the users so they can figure it out themselves, what it is they want to do, and understand how what they're doing is affecting the results. So we would also like to expand our sort of debugging framework to consider these sort of optimizations as well. Now, a couple of other things that we're doing, again, related to an ecosystem, because an ecosystem is obviously bigger than just a debugging framework. So this is actually a pretty small piece of work, but it's something that we've been spending some time on. We have a paper at RAW, it's a workshop coming up in Vancouver in May, focusing on fixed points. So one of the big advantages of FPGA implementations is you can adjust the bit width exactly however you want. If it's on a processor, well, you have certain bit widths you can deal with, and you can do smart things by packing. And I know there's lots of work being done on that. But in FPGA, you can build your data path to be exactly the bit width you want. And there's lots of advantages on that. For inference, clearly small bit widths are known to work well. For training, probably not, although maybe there is something we can do there. And I know there's been a lot of thinking about training within the network right now. So we've been thinking about how we can evaluate different bit widths. Now, we can do it in, so imagine we're designing one of these algorithms. You might start with something like TensorFlow, and yeah, you can specify different bit widths, but there's a limited set of bit widths you can actually consider. At the low level, yeah, when you write your HLS tool, you can specify whatever bit width you want. And the Xilinx tools, for example, have a framework to allow you to do that. But writing HLS-oriented C is time-consuming. So we're spending some time thinking about, is there something in between where we can kind of estimate the impact of changing the bit width without actually having to write the C code, and without having to go and modify, add anything to TensorFlow. So some sort of estimation method. We have something called Kibo, which we've been working on. As I said, this is a relatively small contribution, but it's something that could become important, an important part of the ecosystem as we go on. We've also been thinking about an LLVM flow, and one of the things we'd like to do here is, ideally, we'd like to be able to synthesize networks rapidly from Python. Now, that's a difficult problem. That's even more difficult than synthesizing directly from C. But it turns out that if you look at TensorFlow, there's actually a back-ended TensorFlow where a lot of the TensorFlow framework and instructions can actually be mapped to an LLVM internal representation. So LLVM is a compiler framework that's used. It's used by C compilers. It's very, very common. And it's also used by HLS tools. And the first thing you do in LLVM when you read in the C code is it parses that into this internal representation inside the compiler. Well, it turns out that there's actually utility XLA, which will take TensorFlow and compile that into LLVM. Why is that good? Because HLS tools, like the one from Xilinx and LegUp, which we're playing with, actually can read in LLVM. And so if we have this flow, we could go from TensorFlow to LLVM IR. That could be fed right into an HLS tool. And maybe we could have a fast translation. Now, it won't do everything, but it will do the things in TensorFlow that XLA supports. And that may be enough to really accelerate a lot of the design effort that we would want to do. So that sounds wonderful. It turns out nothing is that simple. There's a lot of sort of modifications to the LLVM we have to make. So we have a tool called LEFlow, which translates the LLVM from XLA into a format that can be used by an HLS tool. This is, there's nothing fundamentally interesting in here. This is kind of an engineering effort. However, it will be very useful if when we get it done, so that we can, more quickly prototype a lot of designs from Python, from TensorFlow. So this is something we're working on right now. We can synthesize simple things, but not complicated things. This is also something we're working with SFU as well. Got sort of two different approaches to solving it. And so we're hoping to get something running and published in the next few months would be my hope here. All right, so that gives you an idea of what I've been doing in the past, and I went sort of a little bit deeper into one of my projects that I think is probably going to be useful for Cohesa. I think underlying all of this is the fact that FPGAs really do provide a unique opportunity for hardware acceleration. They're not as fast as ASICs, clearly, but in a network like Cohesa where we're trying new things, we're not building an ASIC is something you want to hold off until you know that this is really what this is something worth investigating. Initially, FPGAs will provide a lot of the improvements without requiring the expense of building an ASIC. And then in addition, now that they're in the cloud, a lot of times, well, we can just stop there. We can just put things on an FPGA and we'll get sufficient acceleration to investigate a lot of these interesting ideas. To make that happen, I think I've tried to make the case that we need an ecosystem to make this work. And so a lot of the work in Cohesa will be, my work will be to build up such an ecosystem. And I think this is an example of where Cohesa actually can be very valuable, because to make this work, we need these linkages. We need software people. We need domain experts. We need to understand what we can do to make it so that they can take advantage of hardware. And I think through something like Cohesa, we can hopefully make that happen. All right, so that's all I have prepared, but I'm happy to take questions.
Thank you, Professor Wilton. Do we have any questions from the participants?
Yeah, thanks. I'm assuming that is very, very good, very nice. So I think I agree with what you just said, that although ASIC can be faster, it's too early to use ASIC because we actually don't even know what we are trying to build here, right? But later on, if we happen to have a better idea of what we would be building in a chip, I hope there is a way to somehow have it captured in your flow, right?
So there's a couple of things. So you're absolutely right. A lot of this ecosystem actually would apply to ASICs as well. I mean, this is about hardware versus software. So it actually doesn't matter. So a lot of it doesn't matter if it's an FPGA. Some of it does because we're relying on the reconfiguration, but there's probably ways to still be useful for an ASIC. The other thing is, I think there's actually a blurring between ASICs and FPGAs. So one of the things I'd like to look at is different embedded blocks inside an FPGA. Simplest thing, take the DSP blocks, the multipliers, and make them work with small bit widths. That's an obvious, easy thing to do. But maybe there's a lot of other things we can do. And so now you're actually taking an ASIC block and putting it in an FPGA. You can go the other way too. You can put configurable logic into an ASIC. So you can build an ASIC that's somewhat configurable, kind of halfway between an FPGA and an ASIC. So I think the distinction there's actually a blurring between the two.
Yeah. So given that our resources are limited, and like you said, these things are built by big groups, not really research, more sometime goes into implementation. We would probably take the approach that you said. We would probably pick one particular functionality and make a ASIC and use the FPGA infrastructure as much as we can, just for proof of concept, right? So to that end, like the multiplier that you mentioned, what are the other places where we could identify that we could do those functionalities better with ASIC? Like, would you be able to at some point point us those hardwares so that we look for better implementation?
So yeah, I mean, there's a lot of things that we can investigate. One of the interesting things, I know you've been thinking about analog computation. So that's pretty hard to do on an FPGA.
Yeah.
But if you have particular blocks that do some analog computation, it would be interesting putting that on an FPGA. Right?
Yeah. So
you're talking about analog multiplications and adders and stuff. Well, you know, that can actually be a block in an FPGA.
Yes. So the only issue is that, like, you know, it does not, the computation does in phase or in analog domain. Eventually, we have to give you the digital bit. So the interfaces are properly defined.
Yeah.
That would be doable. Is it possible in the FPGA I can somehow use the existing blocks to do the entire computation as well? I am not so familiar with FPGAs inside those DSPs.
So right now the DSPs are pretty limited to performing a multiplication, maybe a multiply add, that's it. And so everything that goes around that is in the normal FPGA logic. So the blocks are pretty small. But that's not to say you couldn't have bigger blocks if we wanted an FPGA specific for these type of applications.
Yeah. So the other thing that often comes are the interconnects, like your memory bandwidth and all that. Are FPGAs good in that, or that is also something being making customized link could make a difference there?
Of course, of course. You're right. Getting to memory off chip is a problem, whatever technology you have. I mean, I'm hoping that you guys can help us figure that out. There are a lot of options for getting memory. For small things, we can store on chip, but anything big we cannot store on chip. There's technologies where you can combine the memory and the FPGA into a package. That could help, but we have all the same problems that a processor would have as well.
Yeah. I mean, this like I have some more. Well, if anyone else have questions, I'd rather leave it to them. If not, I had one or two more detailed questions.
Go ahead. Mazum, please continue.
Okay. So in terms of the memory bandwidth, what do you guys see between the inference and the training? There is a difference in terms of bandwidth and the amount of data. I would say, like, would it be possible to optimize it in terms of reading slowly, but in a very energy efficient way, or reading very fast, but not so energy efficient? Would that sort of customization, would it be beneficial for some of the FPGA computation?
So that's interesting. It's not even just reading memory slowly, it's computing slowly. So a lot of the bit serial stuff that is going on at U of T right now is sort of that way, right? I think it depends on the application. So I did some work with some people at the University of Sydney where we were looking at online training. The idea being that this device was running in the field and it would be doing very slow training as it went. It didn't have to train quickly, it just sort of had to keep up with the environment as it was changing. And so for that sort of thing, yes, if you could read slowly, compute slowly, low power, that would be a good thing. But if we're just training, that's going to require, and inference as well, that's going to require a lot of data, a lot of bandwidth.
Yeah, okay. But I guess, like you said, all this goes to the application, but see, the links are kind of designed for a general purpose, cover everything. So making them reconfigurable, it's a challenge in itself, right? We probably can't optimize too much for one specific application because it's a hardware that would be used for so many different applications, right?
Sure, and that's something the FPGA vendors always have to think about, right? They're not just selling to us. In fact, they're not really selling to us at all. So that, yeah, they have to make that trade-off.
Okay. I already asked a lot of questions. I leave it to others.
Thank you, Mazum. Anyone else from the participants?
Sure. So my question would be, FPGA tooling is famous for being extremely slow to compile designs, and it seems incompatible with a fast debug iteration. How do you deal with that?
Yep, that's a huge problem. I think the two things. So one is incremental compilation is going to be a big deal. Just compiling the parts that have changed. And so we did one study where we used Intel's incremental compilation technology just to recompile the instrumentation that changes between debug iterations. Okay, so not the user circuit. That was fine. That sort of helped. The problem is that a lot of the instrumentation is kind of tapping off signals in the user circuit. And so as soon as you change those taps, the tool says, oh, the user circuit's changed. And so it wants to recompile everything. I think there's a lot more we can do with incremental compilation, and so that's ongoing, is something I want to do. The other approach is the overlay I mentioned, where we compile and overlay once, and it's flexible enough that we can do a lot of common debug tasks without needing a recompile. So that overlay in particular that I didn't really talk about, but just was on the slide, we can change the set of variables the user's looking at. We can change when the user stops the design. And we've actually got one recently where we can make very, very small changes in the behavior of the user circuit, again, without requiring a recompilation of the design. So if we can limit the changes, we can probably build flexibility into the instrumentation such that we don't need the recompile. So I think that may be an approach here.
Okay, thanks.
Oh, okay. I have a question. I think it relates also with the overlay methodology. So just to understand it a little bit better, is it what we're talking about is essentially preemptively, let's say, compiling something that is a little bit more hardware intensive, so as to accommodate picking or tapping different signals by just reconfiguring the SRAM bits, let's say. It's a cascade of multiplexers that, just by reconfiguring the bit streams will, propagate a different set of signals from a predefined bigger set of signals, let's say.
Yeah, so if I put the slide back up here. This isn't a very good architecture diagram to look at, but you can see there's these things labeled overlay configuration bits. There's other ones too that aren't labeled there. Basically, by writing values into those bits, you can control what gets stored in the memory. Nice. So again, it's hard to see here, but this goes to an enable signal, and then there's a flexible line packer. But basically, at runtime, you can change those bits, and we're using Intel's tools, so they have an in-system content memory editor that lets us do that quickly without requiring a recompile, and then we can change what we write. But that does mean foreseeing that is what we may want to change between debug iterations. Foreseeing that, maybe we want to change what variables the user is looking at. If we wanted to change something else, well, then we probably have to do a recompile.
Makes sense, yeah. And in terms of the bit width requirement, which is easier to adjust on an FPGA flow, so the bit width requirement, as you said, it's usually reduced for inference. But also, I think it has been shown that there is variability in the bit width requirement across layers. But I assume the approach here would be to choose the one that rules them all. Is the one that accommodates the worst case scenario, or is that not the case?
So I don't have an answer to that. Our framework would let us explore both.
Okay.
My feeling is no, we should be, because we're doing an FPGA, we should be optimizing every layer as best we can.
Okay. Makes sense. And last thing, I promise, last question. Any thoughts, or maybe you've tried it already, or you're already doing it, incorporating, let's say, a formal layer where in the debugging methodology, where it would possibly reduce the search space in terms of what signals ought to be picked for tapping particular debugging instances and so on?
Yes, that's absolutely part of this that we're looking at. Yeah.
Okay.
I don't have an answer yet.
Okay.
But yes, that is.
Those are interesting research problems. Yeah. Okay. All right. Anything else? Any other question? No?
So I'm available anytime. I'm happy to take questions. And if anyone ever wants to send me an email.
Excellent. Thank you, Professor Wilton, again for volunteering today. It was an excellent presentation, I have to admit. And I think we're resuming May 7th with Professor Shannon, and then May 27th, if I'm not mistaken, with Mazum. Is that right, Mazum? I think
yes.
May 27th. Okay.
May 27th.
Okay. Excellent. And there's going to be proper announcements and everything. So I think we can sign off. Thank you again.
All right. Thank you,
Thanks.
everybody.
Have a good week.
Thank you.
Have a great week.
Thank you.
Thanks a lot.
Bye.
Bye-bye.